Hello everyone, we are going to start the 8th week of this course. What we have been doing from last few weeks is we have derived the formulation for boundary value problems in elasticity. Then we applied the boundary value problems, those formulation to different problems, like we applied to plane stress problem, plane strain problem. In the previous week we applied to different beam bending problems, and in this week we will apply those equations but in a slightly different form to torsion problem. So, topic of this week is torsion. Now, the first two lecture of this week will derive the formulation of torsion. We write the equations, boundary conditions. In a nutshell, we derive the boundary value problem for torsion, and then subsequent weeks we apply them for different problems in torsion. Okay. You see, whenever we start any whenever we learn any theory, or whenever we formulate any theory, one of the most important part of the theory is the assumption. Every theory is based on certain assumptions. Assumption is important because assumptions are essentially limitation of this theory. If you recall, the torsion is, it is not the first time that you are hearing torsion, or we are going to solve some problem in torsion. We studied torsion in our strength of material course, and if I recall what we studied in that course, if you recall, mostly at that time you applied all these formulation to, or you derived the formulation for torsion of a circular shaft. Now, the assumptions that we used in those while deriving that formulation, other than it is elastic, obeys Hooke's law, all the geometric assumptions that we had is, first condition was, if you recall, each cross section rotates as a rigid body about the longitudinal axis. If this is a shaft and this is the longitudinal axis of the shaft, this is the longitudinal axis of the shaft, then every cross section, this cross section rotates about this shaft as a rigid body rotation of this longitudinal axis, about the longitudinal axis. And if this end is fixed, if we take this end is, if we take one end is fixed, then rotation at this end is 0 and the rotation at this end is maximum. And also we assume that rotation of that, as I say, the rigid body rotates about the rigid body, that rotation is linear function of the length, which essentially is the second assumption. The rotation is linear function of x axial coordinate, and this is true as long as our deformation is small. Then another assumption was plane section perpendicular to the longitudinal axis. If we take any section which is perpendicular to the longitudinal axis, any plane section, and then after the deformation, that plane which was plane, that section which was a plane before deformation, even after deformation, they remain as plane. So, these are the very important assumptions that we had while solving torsion or solving a torsion problem, torsion in a circular shaft using strength of material. Now, as just now I said, assumptions are limitations. There are many places these assumptions are not valid. For instance, if we take a case of a non-circular section, for instance, here the example is given as a square section. So, this is the undeformed configuration of the section, and this is the deformed configuration of the section. You see, this first assumption, each cross section rotates as a rigid body about the longitudinal axis, this assumption is not valid in this case. This last assumption, the plane section perpendicular to the longitudinal axis, they remain plane, that assumption is also not valid here. This is the deformed shape, and there is an out of plane deformation. So, this is the plane before the deformation, and that section becomes like this. So, we can see there is some out of plane deformation. Out of plane deformation means deformation, if this is the z axis, then deformation in z axis, in z direction. But in the previous case, in the case of circular shaft, if this was the longitudinal axis, there was no out of plane, there was no deformation in this direction. Okay, that's why there is this. That's why it remains plane, right? But now, in this case for non-circular section these planes do not remain plane. So, first we cannot assume this. So, this assumption is not valid for this class of problems. This assumption is also not valid for this class of problems, right. So, now that was the limitation. These assumptions were the limitation for the approach that we followed in strength of material course, and because of that limitation we cannot apply the same theory to problems with non-circular cross section, because this non-circular cross section, their deformation behavior is such they are not consistent with those assumptions. So, before we start formulating, the first thing we have to do is we have to remove these assumptions. So, these assumptions, this is no longer an assumption for our formulation, but we will stick to this, because as long as deformation is very small, this can be this can be applicable. Okay. Now, so once we discuss the assumption, let us now start deriving these equations. Okay. Take this is suppose a shaft which length is, say this length is L. Okay. And this is how we define the axis. The longitudinal axis is the z axis, and x and y axis define a plane in along the length of the shaft. Okay. Now, take any cross section. For instance, if we take a cross section like this, any intermediate cross section, and this cross section like this. Okay. Now, what happens if we apply some torque here? Suppose if we apply some torque here, say T is the torque, then what happens? This cross section rotates, and our assumption is if this end is fixed, then at this your rotation will be 0, at this end your rotation is maximum, and if you take any intermediate cross section, this is an intermediate cross section. Okay. So, these intermediate cross section also rotate in this direction. So, if we have if we take a section like this, suppose on this section consider any point P which is at an angle theta, and this is the O is the it is the longitudinal axis. Okay. Now, or in this case it is the center of twist. Along this axis it rotates, the rotation takes place. Now, if we apply some torsion like this, now because of this torsion like this, the rotation of this cross section takes place, and suppose the rotation is this. Now, what happens due to this rotation? The P which was initially here, now the P moves in this direction. So, P which was initially at this point, now this P moves in this direction, and this is the new position of point P. I suppose that new position is P dash. So, this is the point, this is the cross section where P is the position, any position before actually deformation took place, and then because of this rotation in this direction, and suppose the rotation is beta, because of the beta amount of rotation, the position P, the point P goes to a new position, and suppose this is P dash. Okay, and this P is taken at a distance of r. Okay. Now, let us see what we will do now is, once we define the rotation like this, now let us see what are the displacement components we have and what are the expression of those displacement components, how those displacement components are related with each other, how they are function of x, y, z. Let us find out that. Now, so take this, this is the diagram. Now, if we see, then P P dash, we can write P P dash as P P dash in this expression. P P dash will be r into beta. Okay. Now, if it is r into beta, so this is r into beta. This distance is r into beta. Now, this is the r into beta is essentially the total component is the total distance that is travelled by p, or the deformation at point p. Now, if we take the component of the deformation in x and y direction, the components will be, if we take the component this is u component and this is v component, v is in y direction, then those components will be u is equal to, that will be minus r beta, then sin theta, and v will be the component y, r into beta cos theta. Okay. Now, this is r into sin theta is essentially y. So, this can be written as minus beta into y, and this can be written as beta into x. So, v is equal to this and u is equal to this. Okay. So, this is how, if we take any point, this is how, because of the rotation of that section, this is how the displacement can be defined as a function of that rotation. Now, you recall we still stick to that assumption that that the rotation is a linear function of the length axis. So, here rotation is beta, length axis is z. So, beta is a linear function of z, alpha z, where alpha is essentially so alpha is essentially beta by z, which means it is essentially the angle of twist per unit length. So, if alpha is the angle of twist per unit length, then this is how the rotation is related to each other. Now, then what we have? We have, if we substitute beta in these two equations, in equation u and v, then essentially what we have is u is equal to minus alpha y z, and then v is equal to alpha x z. So, this is how u and v is related to z. Now, w, which is the out of plane, now one component is still left, that is the w, which is the deformation in z direction, a deformation of that plane in z direction. What we assume is w as a function of only x and y. So, w essentially function of x and y. So, this is another assumption we make, that out of plane deformation on a plane that is function of x and y coordinate, which defines that plane. So, these are the three different displacement components. Okay. So, we will use these three displacement components in our subsequent formulation. Okay. Now, we will come to this point again. Now, if this is the deformation component that we have just now, this 3 deformation component, now let us find out what is the corresponding strain components, and if you recall, the strains are related to displacements as this. Okay. So, this is a linear displacement. Now, if you look at this, so straight away we can make, if we substitute u and v and w in this expression, straight away we can make this is equal to 0, and then del v, and then also we can make del y, this we can make 0, this we can make 0, this also 0, because w is a function of x and y only. And then we have del v del x into del v del u del y, and if you substitute u and v here, we get minus alpha and alpha, and these also become 0. So, all these 4 strain components straight away become 0. So, only non-zero strain components we have then epsilon z and epsilon zx. So, it is a strain component on a plane in z and x direction. It is a shear component of strain. All the normal components are 0. Okay. So, once we have, so this is essentially consequent of this displacement form. Now, let us see, once we have the strain components, what happened to the corresponding stress components. So, these are the strain components we have. Now, this is, if we substitute w here in this expression, from this expression, if we substitute u in this, u and w from this, and u, v and w from this, then what we get is, we get this expression. We get this expression of these are the two non-zero strain components. This you can try, you can verify this. Okay. Now, once we have these strain components, then what are the stress components? Then let us see. The stress, you recall, this is the Hooke's law. This is how the stress and strain are related to each other. Lambda is the Lamé constant and mu is the shear modulus. Now, next what we do is we substitute these strain components into this equation, and then get the corresponding stress components. And if you do that, then straight away we can make all these stresses are 0, all the normal stresses are 0, which is straight away, and the shear stress sigma xy is also 0. Only non-zero strain component is this, and then this will be sigma yz will be this, and sigma zx will be this. Okay. So, then we have, this is the non-zero strain components and these are the non-zero stress components. Okay. Now, let us move on next. So, this is the non-zero stress components. Okay. Now, once we have the stress components, see, we are applying the equations. We are essentially trying to solve different kinds of problem, but the equations which are the governing equations, compatibility equation, those concepts remain same. So, here the governing equations, already we derived the same governing equation we have to use here. This is the governing equation, if you recall. Now, if we write this equation, these are essentially 3 equations, and if we write all these 3 equations, these 3 equations are this. Okay. So, now please note that we already, since that this Cauchy stress tensor is symmetric, so somewhere it is written xz, somewhere it is written zx, both are same. Okay. So, then another condition we impose now, that that since it is only subjected to torsion, we are only focusing on torsion, and we assume that there is no body force in the material. So, if there is no body force, then all these body forces are straight away we can make 0. Okay. Now, so from this straight away we can say all these equations, these equations are, as if you substitute these equations. So, this term will be 0, all this term will be 0, this term will be 0. So, similarly, if you substitute all these expressions, we are left with 1 expression, and that expression is this. Okay. So, this is essentially the third equation of this set. Okay. All first two equations straight away we can make them 0 because of this condition. Now, let us call it, let us say this is equation number 1. So, what is this equation essentially? This is the equilibrium equation. Now, for the assumptions and for the case we are interested in, this equation takes the form this. Okay. Now, once we have the equilibrium equation, then you recall essentially we had 2 equations. One is equilibrium equation, another one is compatibility equation, and then we combine these 2 equations through a stress function. So, let us now derive the compatibility equation. So, compatibility equation becomes, you see, this is the how we got this equation. Compatibility essentially tells you, compatibility equation you can write in terms of strains, you can also write in terms of stresses. How do we write? When we write in terms of stresses, then essentially gives you how the different strain components are related to each other, that we directly get from the compatibility of displacement. Now, once we have that, if we substitute, if we replace strain by stresses, the expression that we have is the compatibility equation written in terms of stresses. So, if you recall, the Beltrami-Michel equation is essentially that, but we won't do, let us not write that equations directly. Let us derive this compatibility equation from the information that we have on the screen. Now, if you look at these 2 equations, is essentially what? These 2 equations essentially we have the definition of strain, and in that definition of means definition of strain displacement relation, and then in that relation we substituted strain, we replace strain by stresses, and we have these two equations. Now let us combine these two equations, and if we combine them, let us do that exercise. If we combine them, then what we have is, first you take the first one, the yz, let us differentiate this one by del x, and then differentiate this one by del y. So, if we do that, what we have is, we have del sigma yz del x, that is equal to mu, and then del 2w del x del y plus alpha. And similarly, this equation gives us del sigma zx del y or xz, that is equal to mu into del 2w del x del y and then minus alpha. Now, if we take this is equation number say A, and this is equation number B. Equation number 1 already reserved for governing equation, equilibrium equation, and if it is equation number B, then let us take B minus A, and that gives you sigma zx del y minus sigma yz, and then that is del x, that is equal to, we have minus 2 mu alpha. So, this is the compatibility equation, isn't it, written in terms of stresses. Let us say now this is equation number 2. So, equation number 1 is the governing equation, equation number 2 is the compatibility equation. These are the two equations we have. So, just let us write equation number 1 once again here. So, okay. So, equation number, let us go to the next slide. So, essentially what we have is, we have this is the equation, these are two equations. The first one we derived from the equilibrium equation, and the second one derived from compatibility. This is essentially a compatibility equation written in a different form. Now, if you recall, then what we did that time, we introduced a stress function. When we solved a plane stress problem, or even in bending problem in the previous week, we solved these equations through Airy stress function. We essentially combine these two equations through Airy stress function. So, here we will not use Airy stress function, we will define a separate stress function, and suppose that stress function is this. So, please note the difference between this stress function and this Airy stress function. Airy stress function, when you define, it was the second derivative of that stress function gives you stresses. It is the first derivative of stress function that gives you stress. In case of when we introduce Airy stress function, as a consequence of that, we got a fourth order equation, which was biharmonic equation. Let us see what we get in this case. So, this is the stress function. Now, if we substitute the stress function in these two equations and combine them, equation 1 and 2, then what we get is, we get this. So, this stress function is called Prandtl stress function, or it is also called warping function. Why it is called warping function, we will discuss in subsequent classes. Now, this equation can also be written as like this. This is essentially del 2 operator. If you recall, del 2 operator was del 2 del x2 and then plus del 2 del y2. So, this essentially gives you del 2 psi is equal to minus 2 mu alpha. This equation is important. So, now we combine all these equations, and finally, we have this equation. This is our final equation. And if you recall, this is Laplace equation is written as del 2, take any function say phi, del 2 phi is equal to 0. If it is homogeneous pi, the right hand side is 0, we call it Laplace equation, and this equation is called Poisson's equation, Poisson equation. Okay, Poisson's equation. Now the thing is, what we have here, you recall in case of when we wrote this in the case of plane strain problem or plane strain problem or bending problem, when we use Airy stress function, our equation was like this. Equation was del 4 phi is equal to 0, but now we have equation this. Okay. So, this is our governing equation, right. Now, essentially what we have to find out, we have to solve this equation for psi, and then once we have psi, to the relation between psi and stresses, we can compute stress, and then from stress we can compute strain and subsequently displacement. But before that, so this is the governing equation. Now, you recall when we talk about a boundary value problems, governing equation is just one part of that problem, and another important part of that problem is the boundary condition. Okay. Now, what we do is, this is the governing equation, we will be using this equation for solving different problems in torsion, but before that let us discuss what would be the form of boundary condition, and that is the topic for next class. So, next class we will discuss boundary condition, how to write boundary condition for the given torsion problem. I stop here today. See you in the next class. Thank you.